Okay, today we get to graph other trigonometric functions, which include cosecant and secant. And here's what we need to know. Sine is equal to 0 for these following values. 0, pi, 2 pi, or any pi times an integer. Forget the box above. We did it yesterday. You guys are super smart. We didn't even need to go to the graphic organizer. You know, as I'm studying graphic organizers for mathematics, you know, for my master's, graphic organizers are referred to sometimes as handout notes. Are these notes helpful to you? Yeah. So, you know, that's one thing that I kind of underestimate as I'm doing my master's. I'm actually next year, I feel bad, but I'm going to take one class through a section of pre-calculus for like a few weeks with no handouts. They just have to write it all down on their own. And the other group I will give the handout to, and we'll just see what happens. Well, I don't, you know, I want to see what kind of impact it has for my master's. Well, one of the pre-calculus classes, I'm guessing. Yeah, yeah. I know. I got to think it through a little bit. So, some people think it's funny. Some people think it's mean. Interesting. Okay. Yeah, I'm not gonna do it for the whole year. Just I want to do it for like a basically like one unit. So we'll see. All right, values for sine and cosecant. So sine is equal to 0 for 0, pi, 2 pi, or any pi times an integer. For example, 79 pi, 80 pi, 81 pi. Any multiple of pi, it will be equal to 0. Well, what's the reciprocal of 0? Undefined. So that means that cosecant is undefined at 0, pi, 2 pi, and not pi to the n, but pi times n. Pi times any integer. So A for the day, if I have undefined values at these spots, what will be on my graph? Vertical asymptotes, the things. Yes, exactly. Vertical asymptotes will run through those spots. So you already know a little bit about the graph. Secant and cosecant are going to have vertical asymptotes because it's the reciprocal of sine, and sine is equal to 0 at some places. So that's a problem. Cosine is equal to 0 at pi over 2, or 3 pi over 2, or 5 pi over 2, or namely any pi over 2 plus pi times n. You don't have to remember any of this up here. You'll be able to graph it without it. No big deal. So that means that the reciprocal of 0 is undefined. And so secant will be undefined for those same spots. Pi over 2, 3 pi over 2, 5 pi over 2, dot, 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 pi over 2 plus pi n. So if it's undefined at those spots, what will I have? Vertical asymptotes at these spots and at these spots for secant and cosecant. That's what's going to happen. We got a picture right now. So true or false? A graph of cosecant and sine are somewhat related. Yeah. If where sine is equal to 0, I have vertical asymptotes, maybe I should draw sine first. So let's do that. Sine goes up to how much? So I'm going to graph y equals the sine of x. Y equals the sine of x. And it goes up to 1, goes down to negative 1. And it has a period of what? That'll be 2 pi, so I mark out 2 pi, negative 2 pi. Yep. Remember, tangent, cotangent, divided into two pieces. Right? We find that period, we divide it in half. Here we find the period we divide into fours because it takes 4 quadrants for sine and cosine to repeat themselves. All right, where does sine start? 0, and it starts by heading up or down? Up. So I'm going to go up to here, cross back over, down, back up. We can generate the graph like so. I need a volunteer. Whitney. Whitney, I'm going to move my pen across, and you tell me when I get to a spot where sine is equal to 0. When do I get to a spot where sine is equal to 0? Yes. Tell me again. Yep. So those are the spots where I have? Yes. It's beautiful. Getting a lot of dots. That's not really a whole lot of fun yet because we want some actual graphs. None of this is actually part of the cosecant graph. In order to generate the true secant graph, I need you to think through this very, very, very important process. It'll take you 2 minutes of critical thinking, and after that, the rest of today will be easy. Watch. I'm going to go to a spot on my sine graph right here. What is the peak of the sine graph? How high does it go? 1. Cosecant is the reciprocal. What is the reciprocal of 1? So there is a spot where the secant and cosecant, or the sine and the cosecant graph actually touch. It's right there. Now, I'm going to follow my sine graph down here. I'm going to point to a spot on my sine graph right here. The height of my sine graph is very close to what? 0. What is the reciprocal of a number very close to 0? Something really big. If you take the reciprocal of, say, 0.1, you get 10. The reciprocal of 0.01 is 100. So the reciprocal of something very close to 0 is something very big. Reciprocal of something close to 0 is something very big. So this is what it does. It touches the max and the mins and heads off towards the asymptotes. So the green is the actual true representation of the graph of cosecant of x. The graph of sine of x and cosine of x are not actually part of the graph. I use that graph in order to generate the true graph of secant and cosecant. So the green is what I'm referring to. Looks pretty complicated, doesn't it? Yeah. The calc kids have totally forgotten how to do that. They'd be like, "What? I don't remember that." You guys know it very well, so good for you. Let's flip over to this page. Find this page. I want to show you something. Samantha Stanley told me something that made my heart jump today. She said that she might want to be a math teacher someday. That made me so happy. Isn't that great? No, she thinks she might want to teach, right? Might want to teach, might want to coach, who knows? Keeping her options open. But she likes so many subjects. What she wants to teach all of them. Well, then my response is, teach elementary. But she likes some of the higher level stuff. So go get a double major. Get your money's worth is what I say. All right. You see this graph here for cosecant of x? This is the true graph. You see the asymptotes there. And whenever you graph cosecant or secant, you should always think to yourself that, lo and behold, right in the middle of it, the whole time, you didn't realize it, there was a sine graph. That's always sitting there. We don't actually draw that. You don't have to, but I just want you to realize that that sits there. That's how that graph is generated. Yeah, it doesn't look like it when you look at secant that there's something there, but in fact, if you truly look at the secant graph, you can see that there is a cosine graph sitting right in the middle of it. And so anytime we graph secant or cosecant, we always want to graph sine or cosine along with it. See the connection? All right, let's graph secant, and then we'll get on the way with the rest of our problems. Secant. Instead of graphing sine, what should I graph? Cosine. Y equals cosine of x. 1 and -1 is my max and min. My period is 2 pi. I mark out 2 pi. So what people get confused with in this class is the periods for tangent and cotangent and then the others. So tangent and cotangent have a period of pi over b, whereas cosine and sine and cosecant and secant have periods of 2 pi over b. And that's a point of confusion. Beautiful. All right, I need a starting point. Where does cosine start? It starts up here at 1. Well, I should draw a pi in there, I suppose, and a negative pi to give myself some type of reference. I start by heading down. I bottom out. My wife made a taco ring for supper last night. You know, like those biscuits that you bake with, like you take them out of the can thing, and yeah, like crescents. Like you put the crescents in like a circle, and then you put taco meat and cheese, and then you wrap it right over the top and bakes in this ring. It's really good. Kids loved it. They thought it was fun. So gotta try different things when you have kids. So all right, I graphed cosine. What do I look for next? Asymptotes, where it crosses over 0. I can see those right here very quickly. Boom. And once I've done that, where do my secant and cosine graph touch? At the maxes and at the mins. What do you think of that? You get it? Let's try some harder ones. Steps for graphing cosecant and secant. Step 1, graph sine or cosine. That's what we start with every time. And so those will be the steps I walk you through. So for example 1, y equals 2 cosecant of x. What will I graph instead of y equals 2 cosecant? Y equals 2 sine of x. That's what I'm going to graph instead. So I'm going to start there. What is my amplitude? 2. And notice I don't use the whole graph for 2 because I know that cosecant will actually rise above further. So I'm just going to mark 2 there, -2 here. What's my period? 2 pi, mark that out. You guys should be very proud. You've learned a lot of trig here in just 3 weeks of school so far. I mean, you've learned all the basics of the unit circle. You learned right triangle trig. You've learned basically all the graphs. That's a lot of learning in a short amount of time. And you guys haven't seen the most fun stuff. When we get law of sines and cosines, you're going to love that. I'm serious. People really like it. Okay, so where do I start? Sine of x. 0. Do a dotted sketch. People ask, do I have to include the dotted sketch on my test? Yes, you do. I have to see that for secant and cosecant. That tells me that you know how to graph it. So I just graphed sine of y equals 2 sine of x. The second step is to work with your zeros and undefined. Draw vertical asymptotes through zeros. So that's our second step. We draw vertical asymptotes through our zeros. The zeros are right where it crosses the axis. Now I've got my vertical asymptotes, and my third step is to draw U-shapes. Whoop, not really through, but at max and mins. Maxes and mins. Maximums and minimums. Now, I would call it a parabola, but it's not a parabola. I'd call it a fourth degree polynomial. It's not a fourth degree polynomial. We don't, I mean, it's a U shape. We don't really have a name for it. I guess there might be, and I may not know it. So, true or false? It touches tangent at that spot. True, because the height right here, again, when we take the reciprocal of 1, we get 1. So it works out there in that situation, okay? Because a parabola would continue on for all real numbers. And this one does not. It approaches the asymptote. So a true parabola would eventually have a value defined for pi. It would continue on. You know, parabolas look like they go up and kind of approach this line, but they don't. They go up forever and they go over forever. So they reach all real numbers on the x-axis. These don't. You know, they don't have that shape. There's other attributes that parabolas have as well, which you guys are going to learn as we move on and study conic sections that these don't have either. Try this one on your own. Okay, I'm going to pause the video. Try this one on your own, then we'll do the last one together. Okay, this is the graph that people came up with. And the question came up about the period. I want you guys to understand that if you look at the other side of the sheet, we talked about how, you know, secant is undefined. It's say pi over 2, 3 pi over 2, 5 pi over 2. But that changes as the period changes. So that's if the period is 2 pi. Well, in this situation, the period is not 2 pi. It's simply pi. And so, so you have an adjustment for where your vertical asymptotes are. So let's do the last one. We're going to change it. We're going to make it look a little bit different. Y equals negative 2 secant of x plus pi over 2 minus 1. Okay, so this really ties together all of your understanding about graphs of secant, cosecant, as well as sine and cosine. And if we want to graph this, again, our very first step is we start by graphing y equals negative 2 cosine of x minus pi over 2, or plus pi over 2, minus 1. So that's what we're going to start by graphing. And when I graph that, what is the first thing I try to identify when I graph sine and cosine? Vertical shift. And the vertical shift is negative 1. So what I'm going to do is I'm going to go down 1 unit. And I'm going to draw an axis through there to help me in my work. The second thing I identify is what is the amplitude? 2. So from negative 1, I go up 2, and I will be at Positive 1 I go down to, and I will end up at. So those are my 2 spots that the cosine graph will oscillate between. Now I identify the period, which is what? 2 pi over b, so 2 pi. So I'm going to mark that out. And then I need to account for a horizontal shift. What is the horizontal shift? Negative pi over 2. And so I'm going to cheat here, you guys, because we've got a lot of dotted things that get drawn in this problem, right? So instead of drawing a dotted graph of cosine right away, I'm gonna graph it right away with the horizontal shift. And now you've had practice, so now I think people can handle this. Where does cosine start on this graph? 1, 0, -3, where? -3. Now watch. That point will get shifted where? Back pi over 2 to right here. And which direction do I head? Up or down? Up. So now I can just start plotting my points for my sketch of my graph. So as opposed to drawing a whole nother graph in there, like we practiced before we apply our horizontal shift, because we've had practice, I feel I can kind of skip that step and move right to this. That will reduce the number of dotted things I have on this graph because it's going to be a lot. So I was able to apply that horizontal shift pretty quickly, pretty easily. Now, the question of the day, this is kind of a finer point here, but this graph actually crosses the x-axis or has zeros at where my finger is right now. But these are not the points that we are concerned about. We are concerned about where it crosses the axis that we drew, because again, everything is shifted down 1 unit. So our vertical asymptotes will go through these spots. So these are the spots that we are concerned about. And now I may finally apply my last transformation, or my last part of my graph, which is to draw the U-shapes at the maximums and the minimums. And I get that shape. Any questions on that last example? Okay, then before I give you your assignment, the last thing I want to do is I just want to show you how to punch in on the calculator. Okay. If you look at y equals -3 secant of 2x, I'm going to graph this one right here, guys. I'm going to graph y equals -3 secant of 2x. So this is how you can check to see if you're doing it properly. I don't know how many times people ask me, Mr. Gens, did I graph this correctly? And what do? I go through all the same sequence of steps that you guys would go through when I check the graph. So an easy way to check your graph is simply to do it on the graphic calculator. It's a great way to make use of this. So let's punch it in. How do I punch in y equals -3 secant of 2x? -3, I don't have a secant, so I go parentheses 1 divided by cosine of 2x. That's how you type that in. Now I'm going to set my window so I see it properly. What is my minimum x value? -pi. What's my maximum x value? Pi. What is my scale? How often do I have tick marks up there? Pi divided by 4. My y minimum value, I'm going to go from -3. I'm going to say -6. I think that's reasonable for that window. and then positive 6. It looks like I have a scale mark every 3 spots up there. So that will match my window that I currently have right there. Once I press graph and I make sure I'm working in radians, which I am, I get that graph. And as you can see, that is identical to what I have. Identical. What's that? You know what I think is really cool? If you go like this, -3 cosine of 2x. Look at that. My calculator isn't as smart as your TI-84's. It shows the vertical asymptotes, whereas yours does not. It knows to remove them. So my calculator is not smart. Anyway, I know you enjoyed it. I'm glad you did. So here's your assignment. It's up on the board, or it's right here, whichever one you want. There you go.